and welcome to session 5 of Unit 2. This session will introduce you to mass defect calculations. By the end of this session, you should be able to solve simple mass defect calculation problems. Let us look at mass defect. Mass defect can be defined as the change in mass that occurs when nucleons are united into the nucleus. Throughout the 20th century, it has become known that mass and energy are interconvertible. When any reaction system releases or absorbs energy, there must be an accompanying loss or gain of mass. It is this loss or gain of mass that is referred to as mass defect. The traditional mass and energy conversion law states that the total quantity of mass to energy in the universe remains constant. So the proportion of mass to energy remains the same. There are no instances that the ratio of mass to energy in the system has changed, that the mass has become more than the energy released, or the energy released has become more than the mass. It is always constant. Mass is related to energy through the Einstein equation E equals mc squared. Now, the m is the mass, c is the speed of light, and we can apply this mass defect or mass equation to examine changes in chemical reactions. So we can say that delta E equals delta mc squared, where delta E can also be said to be change in energy equals change in mc squared. We can make change in mass the mass defect the subject, where we have change in m to be equal to change in E over c squared. So we already said change in E represents energy change, and it is the difference between the products and the reactants in a chemical reaction. You should note that in these kinds of calculations, conversion of units are very important, and 1 joule of energy is equivalent to 1 kilogram per meter square. 1 kilogram meter square per second. Let us look at this example. It says, what is the change in mass when 1 mole of water breaks up into its atom? So this is the equation involved. Water giving us hydrogen and oxygen, and the energy change involved is 934 kilojoule. Now, to address this problem, we first quote the equation for the mass defect, which is change in mass equals change in energy over c squared, that is speed of light square. The energy has been given in kilojoules, so we will convert it to joules by multiplying it by 10 to the power 3. But okay, so change in mass will be equal to 934 times 10 to the power 3 joule per mole over speed of light square. Speed of light is 2.9979 times 10 to the power 8 meter per second. So this is the speed of light, and this is the energy change. We have to move the decimal places forward. That is why the power here has become 5. We move the decimal place back twice, so it changed from 3 to 5. And when we solve for this, we get change in mass to be 1.0 times 10 to the power negative 8 grams per mole. We said that the release of energy and change in mass are not separable, and so nuclear processes are always accompanied by large measurable mass change, and because of that there is enormous amount of energy that is always released during nuclear reactions. And so 1 mole of a nucleus plus the nuclear binding energy, what is holding the particles of the nucleus together, that energy should give us the nucleon. And the nucleon, we know, is made up of protons and neutrons. We shall be looking at mass defect and the atomic mass unit. The mass of every nucleus is less than the sum of the masses of its parts. When you have a particular nucleus and you put the masses of its parts together, the proton and neutrons present in that nucleus together, the sum of these two masses are always bigger than the mass of the nucleus itself. When we consider a typical example in helium, helium has protons with mass 1.673 times 10 to the power negative 27 kilogram, and they have neutrons with a mass 1.675 times 10 to the power negative 27 kilogram. However, the mass of the entire nucleus is 6.643 times 10 to the power negative 27 kilogram, and this is less than the sum of the masses of the protons and neutrons that are present in the nucleus. And this is true for all nuclides. The atomic mass unit, which is simply put as the AMU, the AMU or U, is introduced as a convenient unit for all nuclear masses. It is important to note that 1 atomic mass unit, or 1 U, is equivalent to 1/12 the mass of a neutral carbon 12 atom, and the mass of the carbon 12 atom that is referred here includes the mass of all its 6 electrons. So an example of how the atomic mass unit is used is an example here. The mass of proton, which can be written as 1.0073 U. So the U represents the atomic mass unit. Mass of neutron, which can be represented with U. Mass of electron, which can be represented as U. Let us look a little bit more into mass defect and binding energy. So we stated early on that the sum of masses of protons and neutrons found in the nucleus is higher than the mass of the nucleus itself. So you may ask yourself that what happened to the mass difference between them? Now, the difference in mass between the mass of the nucleus and the sum of its particles is what we refer to as mass defect. We can equally calculate the mass defect of a nucleus by using this equation, change in mass, which is given by the atomic number times the mass of proton plus mass of electron, or plus atomic mass minus atomic number multiplying mass of neutron, and we subtract everything from the mass of the atom. So we have been given the mass of proton, mass of neutron, and mass of electron over here, and these masses are what we substitute into the equation, knowing the atomic number and mass number and mass of the atom itself. Let us look at the binding energy. Binding energy refers to the energy needed to separate the nucleons of a nucleus. To separate the particles of the nucleus, they must be pulled apart against the attractive force that is holding them. Thus, we can see that they have potential energy when they are separated. It is this energy that is known as the binding energy. You may be confused with this, thinking that binding energy is the energy needed to put the nucleon together, but rather binding energy is the energy needed to separate the nucleon. Let us look at this example here, which says that calculate the mass defect for lithium-7. The mass of lithium-7 is given as 7.006003 atomic mass unit. So in doing this calculation, we need to quote the equation for calculating the mass defect of nucleon or a nucleus. Now all the parameters that we need has been provided for. The mass of the atom has been given as 7.01603 atomic mass units, and the mass of the atomic mass of lithium we know is 7. We also know that the proton number is 3, and we've established earlier on the mass of a proton, the mass of an electron, and the mass of a neutron. So we substitute these values into the equation, and we get a mass defect of 0.0421335 atomic mass units. Let's look at transmutation of chemical elements. Transmutation basically means converting one element to another. This can occur naturally or artificially. For artificial transmutation, the first artificial transmutation was carried out by two scientists known as Cockcroft and Walton, where they were able to get helium atoms from bombarding lithium with proton, and that is what is demonstrated here, where this proton is used to bombard lithium and it produces these two helium atoms. So as you can notice from the Cockcroft and Walton's reaction we shown in the previous slide, you realize that the masses are conserved. The masses of reactants are the same as the total masses of the products. We have this example here which says that show that the mass decreases in this reaction, and we've been given a proton reacting with a lithium to give us two helium atoms. And the question continued to say that we should calculate the change in mass, that is, change in atomic mass unit, in kilograms, which means that we have to find the difference in mass and then convert it to kilogram. The first step is to find the mass of hydrogen plus lithium. You realize that the mass of hydrogen is the atomic mass of hydrogen is 1.0073 U, that is atomic mass unit, and the mass of lithium is 7.0160 U. So the total is going to give us 8.0233 U. Then we also find the mass of the two helium atoms, and the mass of helium is 4.015, so two of them will give us 8.0030. Now we find the difference in mass between the product and the reactant, and you realize that after subtracting we get negative 0.0203. This change in mass represents the mass loss in the transmutation process. We need to convert this mass to kilogram. We stated that the atomic mass unit is equivalent to 1/12 the mass of carbon 12, which is given by 1.6605 times 10 to the power negative 22. So we multiply the difference in mass by this value, and it gives us negative 3.3708 times 10 to the power negative 29. So that is the mass defect in kilogram. These are self-assessment questions for your review.